Hello everyone. In this video, let us try to look into the pulse width check of the clock tree. So pulse width check, what we will be doing is we'll be sending the rise edge from the clock port to this particular clock endpoint. We'll send the fall edge from the clock port till this particular endpoint, and then we'll measure the pulse width at the input. We'll measure the pulse width at the output. If they both match, then we are good with the pulse width violation, pulse width check. It's as simple as that. So let us start doing that first. So we have the rising edge pulse, and it goes through a set of repeaters. So for example, this pulse, when it reaches this particular buffer, this buffer again reproduces this particular signal at in this fashion. So basically the buffers, as we discussed in the previous videos, that buffers are nothing but repeaters. It used to repeat whatever is there at the input and at certain distance. So buffers are basically used can be used as repeaters. So this is the rising edge which it receives at the input, and at the output it also generates the rising edge pulse. Let us try to move forward. We'll take this pulse, we'll take this rising edge, and we'll take it at the output of this second repeater, and you see the transition getting a bit deteriorated compared to the input one. It's not as bad as what we saw in the very beginning, but it's slightly greater than what we saw at the input. So yeah, just a point to note, so that's why I'm mentioning over here. Next, what we'll do is we'll propagate it even further. We'll propagate this particular waveform even further and see. So over here, if you see the amount of wire and the amount of wire that it has to take into consideration, or the amount of the load that this particular buffer has to drive, it deteriorates the transition even a bit further. It's not very bad, but it's an average transition that we see over here. Next, we'll take this, and finally when this particular waveform reaches at this particular endpoint, the output waveform that you see is the output transition that you see is not similar to the one that you had at the input, but it's slightly deteriorated. It's not very good, it's not very bad, but it's an average transition from 0 to 1 transition. Now next, what we'll do is we'll take the falling edge of the clock and we'll try to transmit it. So yeah, we have this particular falling edge at the input, at the clock input port, and what we see is once we transmit this through this particular chain of buffers and it reaches over here, we'll find the waveform something like this. So the 1 to 0 transition also deteriorates, but the 1 to 0 transition deterioration is slightly better. It's not as bad as 0 to 1 transition, but it's slightly better than the 0 to 1 transition, but still it has got some finite amount of slew over here, which is not exactly as equal to this one, but it's slightly greater than the one which we sent at the input. So why is that? So first of all, let us check the pulse width now. So the pulse width over here, let's say, is 500 picoseconds, and the pulse width over here, let's say it is not exactly 500 picoseconds, but it's a bit greater than 500 picoseconds. It could be roughly around 700 picoseconds or something like that. So 700 picoseconds at the output, 500 picoseconds at the input. So at the input, if you have a pulse width of 500 picoseconds, and assuming that there is a 50% duty cycle, the other pulse width will also be 500 picoseconds. So totally this comes up to 1 nanoseconds, which is like 1 gigahertz of signal that we expect. At the output, you have like 700, let's say 650-700 picoseconds at the rise pulse. Again, similar number you will be having for the fall pulse. Roughly, let's take the pessimist value, like let's say 700 picoseconds over here, and if you add it, it's like 1.4 nanoseconds. So the inverse of 1.4 nanoseconds will come roughly around 800 megahertz or 850 megahertz, in that range. So what we see is there is a loss of frequency. There is a loss. There is a huge amount of frequency loss which we are gaining at the which you are getting at the clock endpoint, and this loss is a huge loss for a high speed circuit, because high speed we expect it to be 1 nanosecond. It could be more or less 1 nanosecond. It can't deteriorate much than 1 nanosecond. You can consider plus minus 40 ps here and there, but it can't be this bad, because else the purpose of high speed circuits is not getting solved. So what could be the reason behind this? If you see it, the one thing, let us first try to put a cross over here, red cross over here, so that just to make sure by the way, it is not as bad as we saw in the first video, in the first quality check parameter, when we had just built the clock tree without any buffers. It's not as bad as that one, but it's better than the previous one. But it's not the one that we want. So in these cases, what we are doing, we are trying to drive towards perfections, and this is not perfect. This is not a good one. This is not even a bad one, though. It is a reasonable number, but still for a high speed circuit, this is not acceptable. So let us put a red cross over here and try to understand what went wrong. We have taken all precautions. We have put all kinds of clock buffers over here. We are taking care of each and every. We are placing the clock buffers periodically. So what went wrong? So if you closely observe, the rise transition is the first observation over here comes is the rise transition is not equal to the fall transition. That is the very first observation that we see over here. And what could be the reason behind that? Let us put a question mark over here and try to analyze what could be the reason behind the rise transition not being equal to the fall transition. Obviously, there is some physics involved in it. We won't get into that details, but we'll briefly look into why. We'll briefly open up this particular buffer and see what went wrong inside this buffer. Okay. So let us take this particular buffer into consideration, and let us bring out this buffer. And so basically, buffer has got certain properties, but the buffers, we expect certain properties of the buffer. So one particular property of the buffer is performance, and the second one is symmetry. By performance, I mean the speed. The speed is basically whatever you send at the input. At what speed can it send at the output? That is the speed that we expect from the buffer. It should be fast. It should be the fastest. And symmetry is the one that that is the problem for us over here. So symmetrical buffers, which means the rise transition should be equal to the fall transition, which in this case it is not. So in this case, the rise transition is not equal to fall transition, which is actually expected from a special type of buffer. So if we classify these two kinds of buffers, what we see is the regular buffer. There are two kinds of buffers basically. The buffers that are used in the clock path are called as clock buffers, and the buffers that are used in the data path are called as data buffers. So data path is nothing but the path between two flops. It's the data. It's where the data transmits from the Q point of the flop to the D point of the next flop. So basically, the path that you see between launch and the capture, that is the data path, and this is what you see in the this is what you see in the clock path. So clock buffers, it is expected that the regular buffers should be having the performance, or should be showing a better speed, but the clock buffer should be showing a better symmetry. So symmetry is a very important factor for the clock buffers, for this kind of buffers. The performance can be an added feature for the clock buffers, but symmetry is the first thing that basically if you open up any VLSI chip or any VLSI books, you can see, or any VLSI project, if you see, and check out for clock buffers, symmetry of the rise and the fall transition is the one that is expected from the clock buffer, and that is very important. If you see, had this been symmetrical, or for example, had the rise time been better and equal to the fall time, then this would have come a pretty close to each other, and we would have achieved a pulse width which is very close to input. So that could have been achieved if the rise transition was equal to false transition, was equal to fall transition. But in this case it is not. So what we'll do is we'll try to understand from the physics, or not from the physics, from the, we'll open up this particular buffer and try to understand from a resistance point of view what went wrong, what is the problem with this particular buffer, and why are we not seeing equal rise and fall transition. So since I'm running out of time now, so what we'll do is we'll open up this particular buffer. Basically this buffer is nothing but a chain of inverters. So we have to actually understand what is happening with this inverter, what is the resistance values of these inverters, what are the physical properties of these inverters. We won't get deep into the semiconductor device physics because this is not the right place to do that. So we'll be looking into a very abstract view of the inverter and see what went wrong, what is the reason behind having a different rise transition and fall transition. So let us try to do all this in the next video. Thank you.